Hello, ladies and gentlemen. My name is Raziel, and with me here is my research partner, Clarabelle, and we're here to present our journal topic, using deep learning models for insider threat detection within enterprises. Now, in this presentation, we will be going through an overview of our journal, going through everything, from the background information to the conclusion of our experiment. So, onto the background info of our journal. So, what are insider threats? Well, insider threats are defined as security breaches caused by individuals from within an organization. These individuals often have access to sensitive systems and data, which, if sold or leaked, cause both financial and reputational loss for the business. These types of attacks are costly, averaging to 15.38 million USD a year in losses, and have only gained in popularity over the past 2 years. Now, to help detect and mitigate such malicious activities, we can leverage the use of deep learning systems due to their capabilities on how to mimic how a human brain works through the use of artificial neural networks and continuously learn and improve based on data fed to it. To be more specific, long short-term networks, or LSTMs, which are a type of recurrent neural networks which is suitable for our task of detecting insider activity due to its capabilities of handling sequential data, such as log files and user activity in our case. Now, we've compiled a plethora of resources to help us support and guide our research. Now, based on our research, insider threats are usually motivated by the allure of personal gain and a power and access to sensitive data. However, not all insiders are inherently malicious and can be classified into these three categories, depending on the intent of the insider leaking the data. Now, machine learning has been used to detect insider threats, with methods resulting in many limitations, such as high levels of inaccuracy and the inability to utilize and understand complex and nuanced user behaviors, resulting in accuracy limitations. Instead, we use deep learnings instead, which performs better in terms of performance and accuracy due to the utilization of deep layers of nodes, which in turn make it be able to handle larger datasets. As previously mentioned, LSTM's ability to handle sequential data makes it more suited to the nature of the data being used in insider threat detection. Due to its temporal data and behavioral data, it also offers higher performance and accuracy compared to machine learning. Now, onto methodology. We use the CERT Insider dataset version R4.2. It contains over 1,000 users over a period of 500 days and contains multiple simulated insider threat scenarios. Now, for the process, we first start data cleaning, then we follow the process up all the way to modeling. Now, I'll hand the mic over to my friend Clarabelle.
Okay, so for feature engineering, we have two types of feature. The first one, user activity features, that measures the frequency, timing, and intensity of users' actions. And secondly, we have user behavior features that measure the patterns of the user's actions. Next slide. And for the modeling process, we first label the data through data aggregation for user over fixed intervals and sequence generation in order to predict likelihood of individual insider threats. And then we split the data into three subsets. The first 70% we used for training the LSTM network, and then the 15% for validating the model during training and help to monitor the performance, and the last 15% for testing the model independently and gives us an unbiased assessment of the model's effectiveness in real-world scenarios. And for the evaluation metrics, there are four metrics that we use. The first one is precision to help us measure the accuracy of positive predictions. And then the second one is recall. We use to measure ability to identify the threats. And then F1 scores, which is the score to provide a balanced metric. And then the AUC-ROC score to evaluate the ability to distinguish between insider and normal classes activity. And then now for the results. Next. For feature extraction process, there are multiple features that have been extracted. And the first one, the user activity features that quantify the actions performed by users over time. And then the second one, the behavioral features, we have analyzed the user-specific preference, habits, and deviations to provide critical insights into behavior that deviates from established norms. And then the temporal features, which provide a time-based perspective, capturing behavioral patterns over the different time periods as the LSTM model requires it. Next slide. And then for the LSTM model, we use SMOTE to address class distribution as we have a little imbalance in the classes of our data between insider and the normal classes, and distribution to enhance the training process and make the dataset balanced for the model to learn more effectively. And then the model also used Kera Sequential API as it simplifies the implementation of deep learning models like the one used and seamlessly integrates the advanced layers in the LSTM. And then for the model performance, we ran the model and then we also printed the evaluation metrics. Here we can see the score with the ROC AUC score indicates above average effectiveness in distinguishing classes. The precision score indicates moderate effectiveness in correctly indicating correct threads out of flag threads. And then the recall score indicates high effectiveness in identifying actual insider threats. And then lastly, the F1 score indicates high effectiveness in minimizing trade-off between false positive and false negatives. And then as for the classification report, the model printed out the strengths and some weaknesses, and as the strengths lies in the high recall for insider threats, and the weaknesses lies in the low recall for normal activities. Next slide. As for the conclusion, the model has strong detection capabilities at effectively identifying insider threats. However, it is limited as it uses a synthetic dataset which is untested in real-world cases. And then there are areas for improvements as it can be improved to enhance precision even more by reducing false positive. And then for enterprise application, it can be used to reliably monitor routine activities and detect potential threats. And that's all for our presentations. Thank you for so much.